Hi all, this is Claudio from expertfea.com with a new lesson from the series ANSYS FEA from Basics to Advanced. So, a quick reminder about my website, expertfea.com, with lots of simulations, books, and very quick FEA support. My Patreon account, expertfea.com, in which you can gain access for an affordable amount to more than 30 ANSYS simulation webinars or live streams, which total more than 100 hours of FEA masterclass lessons. So, in this lesson, we will discuss and continue what we have done in the third instance of the series. Namely, we're talking about failure criteria and ANSYS SPC dynamics because we're interested in breakage, but in a reliable manner to treat this breakage and what happens furthermore in the plastic regime, let's say, after we pass the yield point. So I have constructed a small PowerPoint in which we need to understand the nature of how the material data is defined and how failure and fracture can appear. So we do have for each material in explicit dynamics, we have a strength model which can present Steinberg-Guinan, Johnson-Cook, or other models. We do have an equation of state, shock equation of state, for example, or Grüneisen. And this is activated when hydrostatic pressure coming from our direction is important, let's say. Then the thing that it's most interesting for us, we need a failure model. This failure model is accompanies these the models from before. You will understand in exactly a few seconds what I'm talking about. For example, if we're going in the explicit dynamics tab for engineering data, explicit materials, we're waiting while the materials are loaded. And for example, if we take the first aluminum material, we can see that is defined or described with the Steinberg-Guinan strength. And you can see here, for example, some graphs, yield versus plastic strain. And the characteristic related to the hydrostatic pressure, which is the shock equation of state. And here you can see a graph plotting the shock velocity versus particle velocity. This is one example. Another example is this one. And please pay attention regarding the strength, okay? So here, for example, we have only shock equation of state. Here we have, again, Steinberg-Guinan. And for example, for this aluminum alloy, we do have Johnson-Cook strength, but we do not have anything related to the failure criteria. Yes? And in a few minutes, you'll understand even more. Let's go back to the PowerPoint. So you have seen strength model, Steinberg-Guinan, for example, or Johnson-Cook strength model. You have seen equation of state, and you will see a failure model. At this moment, in ANSYS, we do not have such failure models applied. For example, let's see. No, this is explosive. For example, for aluminum. I know even for other metallic materials, they are not defined. Instead, we can apply them or define them from here, from this type of failure. It's not active because these are not, let's say, changeable. They can be changed only from here. For example, we do have this aluminum defined with Johnson-Cook strength, but if I double click, we can insert a Johnson-Cook failure, for example. All right, so let's turn back to the PowerPoint. The fourth method, which is mostly visual and it helps the solver, is the erosion control. When we're talking about erosion control, we're talking about this option, this one, geometric strain limit. Normally, it should be left by default, normally. But with experience, we know that we can sometimes decrease it when we know that practical tests break the material earlier, let's say. Yes, so by default the material is left to be broken after 150% strain, let's say. Let's go back to the PowerPoint. So the failure mechanisms are in principle described by their dominance, either stress-based or strain-based cumulative damage, and here we will discuss a little more about Johnson-Cook failure and pressure spot. All right, and this is acting mostly when hydrostatic pressure is being exists. Okay, so each criterion for failure is advisable for example, stress-based for brittle materials, strain-based for ductile materials. This is good, let's say, for ballistic simulations, let's say, or maybe repetitive simulation with a very high rate. And here, as I told, when hydrostatic pressure fails, okay, fails under negative hydrostatic pressure. So hydrostatic pressure crushes or fractures the part that is being defined. This is useful when we have blast, plate, whatever, and fragments are being, let's say, emitted or eliminated. The main, we can also filter more. We have stress-based and strain-based, and we have the differences, all right? These are the differences. We do not have plastic flow here because we deal with brittle materials. We do not care about loading history. Here with strain-based, we do have plastic flow, yielding, and here necking can appear when we're talking about strain-based. Before moving to Johnson-Cook, let me show you one of the simulations. This simulation, I modeled, let's say, a standard specimen, and I have inserted the default, the first aluminum material. In order to review it, you have it here. This is the default aluminum material, in which we have shock UAS linear and Steinberg-Winland strength. Nothing about failure. This is the mesh. And here, I would like you to see that we do not have an end time, which is, let's say, the most realistic one. Realistic would mean, let's say, 1 second or 10 seconds or 100 seconds. Yes, the duration, the standard duration of a pulling test, of a tension test. And we need to decrease this time in order to have a fast solving, let's say. For example, this simulation For 0.02 seconds, the solving took more than 1 hour for 0.02 seconds. If we would have had 0.1 or 1 second, then the solving would have been more extended. And for this, we have used also mass scaling, in which we kind of proposed a time step. Remember these values because they can be useful for linear simulations. In this particular simulation, we kept the default geometric strain limit. One end is fixed, of course, and one is displaced, not force. We don't use a force here. Using a force would imply a shock. Using a displacement kind of removes the dynamic aspect. It's closer to the strength of materials approach instead of the shock, which is a pure dynamic approach, let's say. So this entire specimen is almost 90 millimeters, so the displacement is almost 30%. Let's animate a little and then let's see the results. What is nice here, we do have necking. This is what I promised to you in the last, in the previous lesson. We do have necking. Let me adjust to visible because it wasn't, okay. The value was not correct there. Let's look on the elastic strain with the maximum here. Plastic strain. The stress is pretty small because it's after the fracture, but we do have a big value, let's say, exactly before the breaking. All right. Elastic strain again, maximum principal elastic strain. Then here, remember this is the hydrostatic pressure, which is a compression, all right? So negative of hydrostatic pressure is tension, is extension, yeah? Positive is compression and negative is extension of tension. You can insert this hydrostatic pressure from here, worksheet, and you have pressure somewhere here. Come on. Here, yeah, right click, create user defined result. This is the hydrostatic pressure. Why I'm telling you about this, because this is useful to find out triaxiality. Triaxiality is the fraction, let's say, yes. You can find it as a fraction between hydrostatic pressure. Come on, let me, yes, yeah. So hydrostatic over sigma von Mises, the equivalent stress. This is triaxiality, let's say, triaxiality. Yeah? And we need, in order to have fracture, we need to have a value more than 0.33. Otherwise, if it were less than 0.33, we do not have a fracture, let's say, yes? This being after or more than 0.3, we do have a more complex loading, let's say. Below 0.3, we would have had only one direction. I'm talking about the hydrostatic pressure, yes? So you will see in a few seconds more. So I was talking about traxality, and now we do see some plastic strain. This is a rate that I calculated, yes, in order to see a rate, like a speed for the internal deformation. It's in reality it's effective plastic strain divided by dm times 0.02. This effective plastic strain, you can find it also here in the worksheet. You see it? Look here. Effective plastic strain. Oh. This type of criterion of failure, it's not extraordinary, and it's not, let's say, very reliable, because we do not have defined a failure criterion. I want to remind you, this is the material. We do not have defined a failure criterion here. Instead, look here. The most reliable, which covers most of the failures, is the Johnson-Cook failure criterion, yeah, which describes a damage, which is the sum between the plastic strain and the failure strain. This is the failure strain, which decreases when we increase the stress triaxiality. Yeah, you can see here, sigma m is the hydrostatic pressure over sigma equivalent, which is the von Mises tension. And here, the value 0.3, you can see it here. If we have a uniaxial rod, if we have a value of less than 0.333, then we have only stress on one direction. This is why we need to have a value of more than 0.3 in order to have stress localized at the point of breaking, let's say, in more directions. 1/3 is, you can say, that is the one loading direction. Yes, one stress. But once we exceed 1/3, 0.333, then this necking appears here and it breaks. All right, so this is the formula. Stress triaxiality here, strain rate, and temperature, melting point. Regarding this one, I would like to point you towards this other simulation, in which for the same material, aluminum, the default aluminum 1100, I have added a Johnson-Cook failure criterion. Yes, this one you can see is grayed out. I have asked, for example, in this case from AI, I asked for some values, but normally these values should be given by the material supplier. So this is, let's say, a more complete material because it contains the Johnson-Cook failure criterion defined. And this F, the simulation F, has the results here. So aluminum with Steinberg-Guinan as strength and Johnson-Cook as failure. Again, same fixed support, same displacement. Now let's see the results. We should have maximum 30 here. Adjust to visible. All right. The first thing that you see, and let me tell you, it's not so important. We don't see some necking here because the part is perfectly symmetrical without any notch. In reality, we should create some notch or something. There is the CAD model is perfect, let's say. This is why we do not have a necking here in this when using this material model. All right, failure strain, we do have a equivalent strain, we do have a maximum here. Plastic strain, we should have maximum 0.3. Yes. equivalent for misses, you can ask, hey, why does it break with for when we have so little stress value? And the answer is that you need to also take into account the triaxiality. So it doesn't break only because of the phomesis. It also breaks due to the hydrostatic pressure, which is acting at the point of breaking. Just visible. We do have a peak here at the moment of breaking. This is the hydrostatic pressure that we discussed. Plastic strain rate, triaxiality again, with the remark that positive is compression and negative is retention or extension. And because we have defined a Johnson-Cook failure, you can see it here, Johnson-Cook failure, and only because we have this definition, we have damage constants, only in this case we have the parameter called damage. And when we are close to damage being 1, the material breaks, which is another, let's say, look here. It extended too much, so we can say that this is breaking. For example, here it should absolutely be broken, yes, when the damage is 1. Below 1 normally would mean that it's not broken. This parameter damage is also taken from worksheet, look here, damage O. Right click, create user defined results. The choosing a failure criterion normally takes very much experience. We need to have not only knowledge of FEA and materials, but we need to have practical materials, and we need to perform breaking tests, fracture tests, all right? So remember about the strength equation of state, failure criterion, and erosion maybe. A small remark regarding this last simulation, let's say simulation from F, from the cell F. A small remark, I have decreased the geometric strain limit. 1.5, the default is not always useful, and I know from experience that it should be decreased, because 1.5 was too much for this scenario. Take this into account, all right? 1.5 is not necessarily the best when it shows that the part is enlarged or extended too much or unwanted, let's say. So we have talking about we talked about stress strain damage, a notch is needed or a fillet or something. And by the way, in order to believe that we are in a quasi-static simulation, yes, normally our simulation should be kind of static, yeah, because we are using time explicit dynamics, we are close to static, let's say. We need to kind of check the trend between the kinetic energy and the internal energy. Let me show to you. There is, for solution output, what I call energy summary. And we need the kinetic energy to be very little, very small, Look here, the kinetic energy is the teal one, or turquoise, how it's called, blue, whatever. it should be very small. It is here, there is a peak or something, but this is the measure or the sign that we have a quasi-static simulation, because internal energy is the only one that matters here. Yes? So, and you need to take this into account. If it were vice versa, with a very high value for kinetic energy, then we would have had the shock that I mentioned at the beginning of this lesson, the pulling shock, when we, if we have used here a force, a sudden force for a millisecond or 100th of a second, would have increased the kinetic energy too much. So this is all for my for this lesson, and I will be waiting you in the next one, where we're going to approach and treat the type of compression tests which can be simulated in ANSYS workbench. So please stay tuned, and bye bye.